Okay, last time we started talking about the transient heat conduction, 1D transient heat conduction without heat generation. We derive this equation starting from the differential equation, the variation of temperature with respect to location. Okay. This was our equation. What was the main assumption that allows us to use the lamped capacitance method? Anyone remember? متى نستخدم lamped capacitance method?
Okay. When point number is less than 0.1.
When bio number is less than 0.1. What is the interpretation? What is the meaning of that? Lias, تفضل.
Uniform distribution.
Uniform temperature distribution within the body. يعني كان عندي التغير هذا, this variation is what? 0. Okay, the temperature variation with respect to x we call temperature gradient. Okay, or we have uniform temperature distribution. This was the case when we have just convection. These are the two equations for the lamped capacitance method that you have to know how to use it. The first one, Roman 1, I'm going to call it here. I think equation 5.6 in your textbook, or 5.5, 5.6. This is Roman 2. The first one, we can use it to calculate, to evaluate the time corresponding to a given temperature. The other one, if the temperature is, the time is given and we want to evaluate the temperature, this is the right equation to be used. Also, we define the time constant. Time constant is rho v c, which is the thermal capacitance for the solid itself, divided by the convection characteristic, اللي هي H multiplied by the surface area. The larger time constant, the longer that time required for the body to reach a steady state value. How, as Yasser said, how we can be sure that lamped capacitance method or assumption is right by calculating bio number, which is equal to, which is proportional to the conduction resistance over convection resistance. Conduction resistance over convection resistance. One thing I want you to highlight, and I saw a lot of students understand calculating it, اللي هو characteristic length. As we said, if we have a plane wall, characteristic length is equal to the thickness of the wall. Okay, if we have a cylinder, طبعا احنا نطبق this equation. If we have a cylinder, imagine what is the volume of the cylinder, ignoring these areas اللي هي من هنا ومن هنا. What is the volume? Pi over 4d square L. What is the surface area? Pi dl. These will cancel out. The characteristic length will be d over 4, which is equal to r over 2. For the sphere, also, the characteristic length is equal to r over 3. You have to do the same thing, you're going to get the same result. Okay, bio number, this is the criteria that you have to consider when bio number is less than 0.1. That means the temperature variation, the temperature gradient within the solid medium that we have in our problem is negligible. Any question, guys? Okay. Here is more general or general cases, another section. When we have radiation, if we have heat flux in, if we have heat generation, the ordinary equation will be a little bit more complicated to be solved compared to the previous one. Therefore, here, as it was solved in your textbook, case by case, when we have just radiation term, اللي هو this term, Roman 1, this is the solution. This is the relationship between the temperature, the time and temperature. Okay. Similarly, if we are neglecting radiation, we have the three other terms اللي هي flux applied, heat generation, and convection. This is the solution for that. What is A, B? They are shown in the table in your textbook. You can refer to them. But in this course, we mainly gonna just focus on the convection, when we have convection from outside, and the temperature gradient within the solid medium or within the specimen that we are considered as negligible. These are the two equations that you have to highlight. Okay. باقي الشباب يحلوا الكويز ولا؟ Seems you are still on Microsoft Teams. Are you here, guys? Okay. Okay. Then there is an example, very good, useful example to apply the lambda capacitance method. Here we have a thermocouple junction, which may be approximated as a sphere. This is the sphere which we have. Okay. Which is to be used for temperature measurement in a gas stream. The convection coefficient between the junction surface and the gas H is given 400. Conductivity, specific heat, and density also are given for the solid itself. He is asking you to find and determine the diameter, D, for the sphere, needed for the thermocouple to have a time constant, attack tau, T equal to 1 second. This is the first part of the problem. The second part, if the junction was or is at 25 degrees Celsius initially, خدناها 25 degree وضعناها في الجاز stream which is at 200 degrees Celsius, how long will it take for the junction to reach 199? يعني كان نقول time to steady state temperature. Okay, how to do that, guys? We have two things we have to calculate here. يكون مايك مقفل بس. Can you hear me, guys?
نعم واضح الصوت.
كويس. We still have one student, he's alive. Okay, to calculate the diameter, we have the time constant. We know the equation for the time constant with the rho C volume divided by H surface area. We have to plug these numbers and equate it to 1. We have rho 8,500 multiplied by C is 400 divided by what is the heat transfer coefficient is given in this problem as 400 also. Now what is the volume for a sphere? 4/3 by R cube divided by 4 by RL, right?
أظن المفروض تكون R سكوير ما في.
كويس. We have one student, he is awake. Yes, R square. You're right, yes. This will cancel out with that by with by. 4 will cancel with 4. You're going to have R divided by 3. He's asking us to find diameter. Diameter is equal to 2R, which is equal to 2 multiplied by 3 موجودة هنا, multiplied by 1 second divided by 400 will cancel out with 400. 8500. When you calculate this, the diameter will be equal to, let me bring the number for you, 7.06 10 to power minus 4 meter. Very small. Okay, this is the diameter. Now he's asking you to find the time. Which equation you're going to use out of that two equations which we showed previously? 5.5, 5.6. We're going to use 5.5, okay? Time equal to rho C volume divided by HAS ln Ti minus T infinity divided by T minus T infinity. Now we have to plug numbers. طبعا هذه كلها بنعوضها ب 1 second. Okay. Now initially it was 25 minus 200 T infinity. Here 199 minus 200. This will lead you to 5.2 seconds. This is the time needed for the ball or for the sphere to reach to 199 degrees Celsius. يعني كأننا هنا أوجدنا ال steady state value almost. لأن لو حطينا 200 في المعادلة هذه 200 minus 200 will be 0. We cannot calculate temperature at the time at that point, but we can just take it before we got to the value where a steady state temperature is reached. Any question? This is the diameter. Also, you can check bio number. You can calculate bio number to be sure that the lumped capacitance method is applicable or can be used. When we calculate bio number, it will be 2.35 10 to the power minus 3. Okay. Here is a conceptual question about the same problem for the thermocouple. A question for you: when we have the same thermocouple, a sphere, and we have two different tests or two different systems. One of them, we put that sphere on an air as a medium. The other one in a water. The heat transfer coefficient for the water is 80 watt per meter square Kelvin. The heat transfer coefficient for the air is 10 watt per meter square Kelvin. The temperature is the same. The size of the sphere is the same. The material, both of them were built from copper. The question: which one do you think gonna reach to a steady state value? طبعا steady state value عندنا هي 40. In which case the ball or the sphere gonna reach to a steady state value faster than the other one? Water or air? Nothing. الافضل نخلي الكويز في second part of the class, maybe better. Just to, I don't know, where are you? Maybe the students still shocked about the quiz. Quiz was not difficult. Okay. Which one? سمعت صوت كده.
Water.
Water. Why? Because the heat transfer coefficient is higher, time constant is lower. We know that when time constant is lower, it needs less time. لاحظ معي هنا around 40 seconds. That means this is the steady state time. Air still خلصنا دقيقتين تقريبا. Still it did not reach to the value of steady state. Steady state value is 40 in both cases. If you put the equation, this is the variation of temperature with respect to time. Okay. Any question about it? Now, if we have a spatial effect, this is the second part of this chapter. The first part, when the temperature gradient is negligible, lamped capacitance method. هنا لما يكون عندي البايو number is greater than 0.1, that means the spatial effect means the temperature will be changing with respect to x, will be changing with respect to the location. Therefore, this partial differential equation should be solved. To solve this partial differential equation, you know it's the second order with respect to location, first order with respect to time. That means we need two boundary conditions. This is one. This is the second boundary condition. And we need one initial condition. This is the initial condition. On the problem of that, when we would like to solve this partial differential equation, we have around 8 independent variables. Temperature is function of x, location to function of temperature, function of the initial temperature, T infinity, L, K, thermal diffusivity alpha, and H, heat transfer coefficient. To simplify the equation, to be able to solve it, it's quite similar to the similarity problem. If you remember the similarity analysis which we have done in fluid mechanics, you simplify a long equation with several variables to try to find the relationship between these variables. This is what we have done here in this part. We introduce, we call it a dimensionless temperature, theta, which is equal to theta divided by theta I, the initial temperature difference. xi is nothing but it's dimensionless location. هي عبارة عن equal to 0 here, equal to 1 at L, equal to -1 at -L. The third one is which we call a new one, which called Fourier's number. Fourier's number is proportional to the time. Alpha thermal diffusivity multiplied by the time divided by L squared, the thickness of the wall square. Now, to solve that equation, we have to just modify the boundary conditions, these two boundary conditions and the initial condition. You don't have to do that. You don't have to know the steps. All why I brought this here to you, that by introducing these three independent dimensionless parameters, we moved our equation from 8 independent variables to a 3, which are x star, Fourier's number, and Biot number. Now, solving this equation will lead you to something which is a little bit complicated, but just I want you to know how to use that equation. That equation is a relationship between theta, اللي هي temperature, and time, which is Fourier number here. الآن التايم عندنا implemented. This is the time. This is the temperature. Okay. Just to summarize what we have said, and then we're going to see the solution of this equations or differential equations. First of all, when we have any problem that time is involving, you have to evaluate the Biot number. If Biot number is less than 1, go to Lamb capacitance method, section 5.1 and 5.2. مباشرة. First, you have to calculate Biot number. 1. لو Biot number is greater than 0.1, I have to go to the exact method, which you're going to see now. Exact method, you have to calculate Fourier number first. If Fourier number is less than 0.2, you have to go to, I will call the complicated solution. Like in the course هذا, in this course, we will not deal with that, just for simplicity. Okay? Most of our cases is going to be having Fourier number which is greater than 0.1. لما يكون عندنا Fourier number greater than 0.1, we can use what we call truncated series solution, one-term solution. Also, I'm going to explain to you in the next slide. الأهم هنا لما تدخل في الexact method, you have to recalculate البايو number again based on these two equations. طبعا في البلين وول ما اختلف معايا القيمة هنا والقيمة هنا، لكن في الcylinder والsphere it will be changed because the characteristic length here was for cylinder r/2, for sphere r/3, but when you calculate Biot number for the exact method, it should be multiplied by r, not by that characteristic length. The solution of the previous differential equation is this. Might be scary, you might be afraid when you see these equations, but let's take it part by part. Inshallah, we're going to talk about this more in next class. This is the solution when we have a plane wall. Okay, we have exponential, we have cosine. What is xi? طبعا لاحظ معايا, this is theta, the temperature at location. This is the location, and also at instant time. This is the time. But at each second we have different distribution. Okay, we have two variables here, time Fourier number and x, which is the location where you would like to find the temperature. Is it at the center line? Is it at the surface? Is it somewhere in between? These are the things. These eigenvalues are provided to you in tables. You have just to go, also this constant, you have to go to the table and get them from there. Like in this course, we will not be having a Fourier number less than 0.1. Most of the case will be greater than 1. Greater than 1, I don't have to solve the whole series. I have just to take the first term. Also C1 and the first eigenvalue are provided in the table. Fourier number is, again, which time we would like to calculate the temperature at and which location is we would like. Inshallah, we will solve an example for the sphere, which is more challenging compared to the plane wall next class. These are the tables which I just mentioned. Based on the Biot number, you will pick the right value of the eigen value and the right value of C1 and just plug it in that equation. You're going to have a temperature distribution as function of time and as function of location. We're going to start, inshallah, from this slide next this Sunday, inshallah, next lecture. Okay, if you don't have any question,
خرج الدكتور.
شكل خرج.